Firstly, in real case, the exponential function is equal to es. So let's apply this is in complex case. Thus, the exponential function is equal to e to the power of z. We know that z is equal to x plus I theta. Then we apply from this, we get e x plus I theta. From Euler equation, we know that e I theta equal to cos theta plus I sin theta. So from this we get Ez equal to e x cos theta plus I sin theta. Next, we talk about the properties in exponential function. We look at the graph. Firstly, we assign that this is the point. Now, the length is here is e to the power of x. The x-axis here is ex cos theta. Before that, we should know that this is theta. Then, for the y-axis is ex sin theta. First case, so we should add I. Then the point here is ex cos theta plus the y-axis is ex sin theta. We factorize the ex, so we get cos theta plus I sin theta. From this, we know that this is Ez. So this is equal to e to the power of z. For the magnitude of Ez is equal to ex from here. This is the second property of Ez. The third property is e to the power of z never be 0. Let's say Ez equal to 0. So we know that Ez equal to ex cos theta plus I sin theta. To get 0, it should be either is 0 or this is 0. But in real case, ex cannot be 0 because from the graph, we know that ex is approaching 0 but never be 0. Next, if the second component is 0, both cos theta and I sin theta should be 0. But it is impossible as theta equal to 0, cos theta plus I sin theta is equal to 1. So, Ez never be 0. This is the third property for e to the power of z never be 0.
Okay, we are near to the end of our discussion. Now I will tell you about how to get roots for exponential function. Ez is equal to ex cos theta plus I ex sin theta. So the root here is z, and as we know, z is equal to x plus I theta. So this is our first equation. For the Ez is equal to ex cos theta plus I ex sin theta. We assume this part is A and this part is B. So ex cos theta is equal to A, while ex sin theta is equal to B. Now, we square the both sides. The same goes to this part. We square the both sides also. Next, we add this both part. So e to x cos squared theta plus e to x sin squared theta is equal to a squared plus b squared. Rewrite the equation. E to x is equal to a squared plus b squared. To get the x as the subject, we multiply both sides with ln. So we will get 2x is equal to ln a squared plus b squared. We leave the x here, so we will get 1 over 2 ln a squared plus b squared. This is our second equation. From the start, we assume ex cos theta is a and ex sin theta is b. So if b over a, where a is not equal to 0, then b over a is equal to ex sin theta over ex cos theta, which is equal to tangent theta. Get our x. Now we left out with theta, so we want to find what is theta. So theta is equal to arctangent b over a. So this is our third equation. Next, we derive the formula z is equal to x plus I theta. So we put in the 2 and 3 equation into this equation. So we will get z is equal to 1 over 2 ln a squared plus b squared plus I arctan b over a. So for the general equation, the root, which is z, is equal to 1 over 2 ln a squared plus b squared plus I arctangent b over a plus 2 pi k, as the function ez is periodic. That's all for the exponential function in complex analysis.
To define log z as the inverse of the exponential function, first we assume these properties is fulfilled. That is, if z1, z2 and p is any complex numbers, then log z1, z2 equals to log z1 plus log z2. Log z to the power of p is equal to p log z. For the example, we use w equals to log z if z equals to e to the power of w. For w, where z is any non-zero complex number, we write w equals to u plus iv. Then the equation of z equals to e to the power of w become this. Oh wait, how do we get this equation? This is the first question. Before we get started, you must know that log z equal to ln absolute of z plus I argument of z. Let's start with log z1, z2 equal to log z1 plus log z2. Log z1, z2 will be equal to ln absolute of z1, z2 plus I argument of z1, z2. From ln absolute of z1, z2, we can write further as ln absolute of z1 plus ln absolute of z2. For I argument of z1, z2, we can turn it into I argument of z1 plus I argument of z2. Next, we must rearrange it as ln absolute of z1 plus I argument of z1 plus ln absolute of z2 plus I argument of z2. Therefore, we can conclude that log z1 z2 equal to log z1 plus log z2. Next, we verify log z1 over z2 equal log z1 minus log z2. Log z1 over z2 is equal to ln absolute of z1 over z2 plus I argument of z1 over z2. From ln absolute of z1 over z2, we can write further as ln absolute of z1 minus ln absolute of z2. For I argument of z1 over z2, we can write as I argument of z1 minus I argument of z2. Then rearrange the equation in this way. Ln absolute of z1 plus I argument of z1 minus ln absolute of z2 minus I argument of z2. From that, we know that ln absolute of z1 plus argument z1 is equal to log z1, and ln absolute of z2 plus argument of z2 is equal to log z2. The next question is, show that if z1 equal to I and z2 equal to I minus 1, then log z1 z2 is not equal to log z1 plus log z2. We start with left hand side. Log z1 z2 is equal to log I times I minus 1. Then it becomes log I squared minus I, which should be written as log negative 1 minus I. Next, log negative 1 minus I is equal to ln absolute of negative 1 minus I plus I argument of negative 1 minus I. From the graph as shown, we get the argument of negative 1 minus I, that is pi over 4 minus pi, or negative 3 pi over 4. The absolute of negative 1 minus I, we get surd 2. Thus, log negative 1 minus I is equal to 1 over 2 ln 2 minus I 3 pi over 4. For the right hand side, firstly we write log z1 plus log z2 is equal to log I plus log I minus 1. As we know, log I is equal to ln absolute of I plus I argument of I, whereas log I minus 1 is equal to ln absolute of I minus 1 plus I argument of I minus 1. For ln absolute of I plus I argument of I, we get ln 1 plus I pi over 2, whereas for ln absolute of I minus 1 plus I argument of I minus 1, we get 1 over 2 ln 2 plus I 3 pi over 4. Now we solve the equation and we get the final answer, that is 1 over 2 ln 2 plus I 5 pi over 4. As we can see, log z1 z2 is not equal to log z1 plus log z2.
Hello everyone, I am Dr. Yati. So today I'm going to teach you about complex power. Complex powers. We can write the general form of this function as z to the power of c, which is equal to exponent c log z, and z cannot equal to 0 because this part will be undefined. With log z equal to ln modulus of z plus argument z plus 2n pi I, which equal to capital log z plus 2n pi I, n is any whole number. Now, let's take a look at the first form. If c is not a real rational number, Then, this function has infinite solution. The value for z to the power of c equal to this is the principal value for this function. Now, let us take a look at example 1. Get the value for 1 plus I to the power 1 plus I. 1 plus I to the power 1 plus I equal to e 1 plus I log 1 plus I. And then we solve for this part, and then we know the argument for 1 plus I equal to pi over 4. And then we get e 1 plus I ln set 2 plus pi over 4 pi. The second form, if c is a rational number, let's say c equal to m over n, and m is any integer number, and n is any positive integer number, then this equation only have different values for n. Then we get z to the power of n divided over n, we get exponent m over n log z e m over n to pi ki, which is k is from 1 up until n minus 1. Now, let's us look at the example 2. Get the values for 1 plus I to the power 1 plus I over 2. This is equal to this, and then we solve for this part. We know that the argument for 1 plus I is equal to pi over 4. And then we get e to the power of 1 plus I over 2 ln set 2 plus pi over 4 plus 2 pi k I. K is 0 and 1 because the n here is 2. Okay, now let us take a look at the two main characteristics of complex power function. First, if z is not equal to 0 and c1, c2 are any complex number, then for the principal value, z to the power of c1 times z to the power of c2 is equal to z to the power of c1 plus c2. Second, if c1 times z2 to the power of c is not equal to z1 power of c, z2 power of c, except for argument z1 plus argument z2 is between negative pi and pi. And then z1 over z2 to the power of c is not equal to z1 power of c over z2 power of c, except for argument z1 minus argument z2 is between negative pi and pi. Example 3. Let z1 equal to 1 plus I, z2 is equal to I, and c is negative I. Show that z1 times z2 power of c is equal to z1 power of z, z2 power of c. First, we must find the argument of z1 and z2 to check this condition. We know that argument z1 is pi over 4. And the argument for z2 is pi over 2. Then we know that the argument of z1 plus the argument z2 is equal to 3 over 4 pi, which is between negative pi and pi. We solve for this equation. First, we solve for the left-hand side equation. The left-hand side is z1, z2 power of c. We multiply the z1 and z2, we get this. And then we solve like usual that I have teach you earlier. And then we get z1, z2 power of c is equal to e to the power of 3 over 4 pi minus I sine ln sec. For the right hand side, we solve for the z1 to the power of c, which is equal to 1 plus I to the power of negative I. And then we solve for this and we get this answer. Then we solve for the z2 to the power of c, which is equal to the I to the power of negative I. And then we get this answer. Then we multiply then we multiply those two, and then we get the same answer as we get here. Then we can conclude that z1 z2 to the power of c is equal to z1c times z2c. Okay.
Thank you so much, Dr. Yati. Now I understand this topic better. But I still have two questions for you. First question is, what is the derivative of complex power function? And my second question is 1 raised to any power still always get 1? I have that question that I still cannot figure out. Can you answer that question, Dr. Yati? Thank you.
Good question, Ridauddin. Now, let us discuss. First question, the derivative for the complex power function. First, the derivative of this function is equal to e z log z times c over z. The differential of here is this. And then we know that this part are c to the power of c. We simplify this, we get c to the power of c minus 1. So this is derivative for the complex power function. For question 2, is 1 raised to any power always equal to 1? For solving this question, we write 1 raised to any power, let's say alpha. And we solve this, we get e alpha log 1. And we solve for this part, we know that the argument for the log 1 is 0. As you can see here, there is no argument. And then this part also equal to 0. And then when we multiply this part, we will get e to the power of 0, which is equal to 1. Therefore, we can conclude that 1 raised to any power always equal to 1.